Welcome to the AE3610 Supersonic lab. This lab consists of two different parts. First, the CD nozzle, converging diverging nozzle, and then the blow-down tunnel. First, let's look at the equipment for the converging diverging nozzles. So, we have the air coming through a pressure tank outside of this room. It goes through all these pipes right here. So, we have different valves to control the flow. We also have pressure gauges to control the pressure inside the test section. So the air goes then into the test section. The test section is separated in two different parts, so the converging part and then the diverging part. You can see the different pressure tabs and pitot probes inside the test section. If you want a closer description of these of their locations, you can look at the figure 5 of the lab manual. And so then the air goes through the acoustic muffler right there, and it finally goes into the room pressure. So the main thing we'll record during this lab is the 8 pressure coming from the pressure tabs right there. So it's connected to all pressure transducer right here. So then you have two other pitot probe at the upstream and downstream of the converging diverging nozzles, which are also connected to these two pressure transducers. These pressure transducers are some diaphragm type pressure transducers. They are then connected to, they give us voltage from the pressure measurements from the pressure tabs and the pitot probes. They are then connected to the two National Instrument DAC boards right there. And these two DAC boards are connected to the LabVIEW VI right here, which show you the raw voltages for each pressure type and pitot probes. And we can also transform these raw voltages into PSIG value using the datasheet. So it means like the sensitivity and the null offset of the pressure transducers. You have seen in the previous video that we can see both the voltages and the pressure from the pressure transducer on the computer, but we don't trust perfectly the datasheet that we use to calculate the pressure coming from the voltages, so we'll use our own calibration process. The calibration process will be done using this calibration box, where we can know the pressure using this pressure gauge right here. This pressure comes from the high pressure supply that we've presented before. It can be controlled using this valve. And so then we will go during the calibration process to the values of 14 PSIG, 7 PSIG, and 0 to calibrate each pressure transducer right there. The value you'll get on the calibration Excel file will be the value of each pressure transducer voltage coming from each value of PSIG from this pressure gauge. We'll show you only the print screens of each value, as the process for doing this calibration is pretty loud. So in the previous video, we've seen the calibration process of the experiment on the CD nozzle. In this video, we'll explain you the real experiment on this supersonic converging diverging nozzles. So we'll increase the pressure with this valve right here during the experiment. As you can see, when you quickly increase the pressure right here, it's going to be very loud. So we won't record any sound for the next video while we run step 6 to 8 of the procedure. So then I want to explain you how does the LabVIEW work for this part of the lab. So we transform it slightly compared to the calibration process. So we now have stagnation pressure on one part on the left hand side. So the scale has been adjusted to refer to the shock waves in the test sections. So as you can see, it goes from 0 to 40 for the stagnation pressure and from -10 to 20 for the static pressures. On this video, we'll go through steps 6 to 8 of the lab manual procedure. We'll gradually increase the pressure inside the seal nozzle by turning the red valve over there. At each point, we'll just save the data and take a screenshot to make sure you understand at which section of the lab manual it corresponds to. So we'll start by increasing the pressure inside the wind tunnel. Slightly more. Okay. Oh, go slightly back. More back. Much. Other way. Increase. So now the flow is subsonic. We take data and we take a screenshot. So now, I'll go back more, little more, okay. So now the flow is just short, take data, now the shock in the region B is between static step 4 and 5. Take data. And now the shot is after static step number 6. And now we'll just stop the experiment. In the second part of this lab, we'll use another supersonic tunnel, the blowdown tunnel right here. So it's also connected to a high pressure supplies in another part of the room. So it gives pressure to the pipe right there, we can control the pressure inside the blowdown tunnel by looking at the pressure gauge upstream. And what we'll do during the lab, we'll just put 3 different plates, which consist on one pitot probe and static tap, one variable area diffuser right here, and one wedge. So the main thing with this setup is that we can both measure the pressure on the pitot probe and the static tap by using baratron, which is another pressure transducer that you've used in your previous lab, connected to a voltmeter right here. And we can also visualize the oblique shock when we put the wedge into the test section with this screen right here. So so we can visualize it with the Schlieren technique, which consists on several lenses and screens to visualize the difference of the gradient of density due to the shock waves. So now we've just put the pitot probe inside the blowdown tunnel, so we'll record the stagnation pressure first using the voltmeter right here. So we'll connect the baratron to the voltmeter. So when it should be atmospheric pressure on both sides of the baratron, the value is 0.04. So it means
negative 0.04.
Negative 0.04. So you need to take that into account in your future calculations. So we'll just open the pressure in the blowdown tunnel right now. We'll go to 14 psi, and I'll give you a thumbs up when we'll reach this value. So you can record the stagnation pressure voltage on the voltmeter. So now we switch to the static port on the pitot probe. So we're just gonna repeat the exact same experiment. Now we've done stagnation and static pressures with the pitot probe inside the blowdown tunnel. We'll use the variable cross-sectional area diffuser right here. So we'll modify the cross-sectional area inside the test section by screwing right here. So it will increase the angle of the plate right here and reduce the cross-sectional area inside the test section. So what we'll do while running the experiment is just increasing the pressure over there at the same 14 psi pressure we've done previously, and we want to find a point where we feel the shock on the screw right here. So this shock will be found by feeling strong vibration on this screw. Once we've found this shock, we can measure the cross-sectional area of the test section by measuring the width and the height of the plate and the test sections using calipers.
And we'll give that to them.
And we'll give this value. So the last part of the blowdown tunnel consists of putting this wedge into the blowdown tunnel. So when you put this wedge into a supersonic flow, you will see an oblique shock that will be created over there, and so we'll be able to see this oblique shock on the screen over there of the Schlieren setup. And we'll also be able to record the static pressure due to this static tap on the voltmeter, like we did for the pitot probe and the static tap in the other class. So we'll see the oblique shock on this screen. So you'll see different colors for different for the shock, which correspond to the change of density inside the test section.
Okay. And now we're increasing pressure to 14 psi.